The story of artificial intelligence begins long before computers filled rooms, or algorithms sifted through data at lightning speed. It starts with a fundamental human question: can machines think? This isn't just a modern curiosity. For centuries, philosophers and inventors have wrestled with the idea of replicating human reasoning through mechanical means. In ancient Greece, thinkers like Aristotle laid the groundwork by formalizing logic, the principles that govern reasoning and argument. Aristotle's syllogisms, simple logical statements that connect premises to conclusions, hinted at the possibility of a systematic approach to thought. Centuries later, this idea of formal logic would become the backbone of early AI. Fast forward to the 17th century, and philosophical giants like Leibniz imagined a universal calculus, a symbolic language meant to resolve disputes through calculation. Leibniz believed that reasoning could be reduced to mathematical operations, a notion that would resonate deeply with the future of computing. Alongside these ideas, the concept of automata, mechanical devices designed to imitate living beings, captured the imagination of inventors. From intricate clockwork figures to mechanical birds, automata illustrated early attempts to mimic life's complexity through engineering. These creations were less about intelligence and more about movement and illusion, but they set the stage for a deeper inquiry into what it means to simulate thought. The true turning point came in the 20th century with the work of Alan Turing. Turing was not just a mathematician, he was a visionary who saw computation as a universal process. In 1936, he introduced the concept of a universal machine, what we now call the Turing machine, a theoretical device capable of simulating any algorithmic process. This was a profound leap. It meant that a single machine could, in theory, perform any computation given the right instructions. Turing's insight laid the foundation for modern computers and, crucially, for artificial intelligence. During World War II, his work on codebreaking demonstrated that machines could tackle complex problems once thought to require human intuition. But it was his 1950 paper, Computing Machinery and Intelligence, that formally posed the question of machine intelligence. In it, Turing proposed what became known as the Turing test, a way to evaluate a machine's ability to exhibit human-like intelligence through conversation. The Turing test wasn't just a challenge. It was an invitation to explore intelligence as a measurable, testable phenomenon. This shifted the discussion from abstract philosophy to practical experimentation, setting the stage for the first wave of AI research. By the mid-1950s, the idea of artificial intelligence had gathered enough momentum to bring together some of the brightest minds in a landmark event. In the summer of 1956, at Dartmouth College in New Hampshire, a small group of researchers convened to explore the possibilities of creating thinking machines. This gathering, now known as the Dartmouth Conference, is widely considered the birth of AI as a formal field of study. A proposal for the conference was ambitious. The organizers believed that every aspect of learning, or any other feature of intelligence, could, in principle, be so precisely described that a machine could be made to simulate it. This optimism captured the spirit of the era and set the research agenda for decades to come. Among the early successes that emerged from this period was the logic theorist, developed by Alan Newell and Herbert A. Simon in 1955. This program could prove mathematical theorems, mimicking a human's approach to problem solving. It wasn't just a demonstration of raw computation, it was an attempt to replicate the reasoning processes underpinning logic. Following this, Newell and Simon created the General Problem Solver, or GPS, designed to tackle a wide range of problems by breaking them down into smaller, manageable steps. GPS embodied the belief that intelligence could be understood as a series of logical operations, applicable across different domains. These early programs were limited by today's standards. They operated within narrow, well-defined tasks and struggled with ambiguity or real-world complexity. But they were crucial proof points. They showed that machines could, in fact, handle tasks that required reasoning, even if only in constrained environments. The foundational ideas from this era also revealed a tension that would define AI's trajectory. On one hand, there was the symbolic approach, using logic and formal rules to represent knowledge and reason about the world. On the other, there was an emerging awareness that human intelligence might not be fully captured by symbolic manipulation alone, hinting at the complexities that lay ahead. During these formative years, AI was as much about philosophy as it was about engineering. Researchers debated what intelligence really meant and whether it could be distilled into algorithms. The field was built on the hope that with enough understanding and computational power, machines might one day replicate human thought. Yet these early milestones were only the beginning. The ideas of logic, reasoning, and universal computation provided a framework, but they also exposed the challenges inherent in mimicking the mind. As AI moved beyond the 1950s, it would have to confront questions about learning, perception, and adaptation, questions that continue to shape the field today. The origins of artificial intelligence remind us that this quest is deeply rooted in human curiosity about thought itself. From Aristotle's syllogisms to Turing's universal machine, each step has expanded our understanding of what it means to be intelligent and what it might mean for machines to share that trait. In the next chapter, we'll explore how these early theories evolved into practical systems and how the field grappled with its first major hurdles. The journey from symbolic logic to the complexities of real-world intelligence is a story of ambition, setbacks, and breakthroughs, one that continues to unfold. The story of artificial intelligence in the 20th century is one of ambition, setbacks, and reinvention. It begins in the mid-20th century when the idea of creating machines that could think like humans captured the imagination of scientists and the public alike. Early researchers believed that intelligence could be broken down into a set of logical rules and algorithms. This belief sparked a wave of optimism, particularly during the 1960s and 70s, when the first AI programs showed promising results. During this period, pioneers like Alan Newell, Herbert Simon, and John McCarthy pushed the boundaries of what machines could do. They developed programs that could solve puzzles, prove mathematical theorems, and even engage in simple conversations. The excitement was palpable. Computers were becoming more powerful, and it seemed only a matter of time before machines would rival human intelligence. But this early enthusiasm ran into unexpected difficulties. The complexity of real-world problems proved far greater than anticipated. Simple rule-based systems struggled to handle the ambiguity and nuance of everyday situations. The limitations of these approaches became clear, and progress slowed. Funding dried up, and public interest waned. This period of stagnation is often referred to as the AI winter. The first AI winter in the mid-1970s was a sobering moment. Expectations had outpaced reality. Projects that once seemed groundbreaking failed to deliver practical results. The optimism of the previous decade gave way to skepticism. Researchers began to question whether the original goal of general artificial intelligence was achievable with the tools and knowledge available at the time. Despite these setbacks, AI research did not disappear. In the 1980s, a new approach emerged, centered around what came to be known as expert systems. These systems aimed to encode human expertise in a specific domain using a large set of rules. Instead of trying to replicate general intelligence, expert systems focused on practical applications, such as medical diagnosis or financial decision-making. Expert systems enjoyed a period of commercial success. They demonstrated that AI could be useful in certain contexts, and businesses invested heavily in them. Yet, this success was also limited by the inherent weaknesses of rule-based systems. They required extensive manual input to create and maintain the knowledge base. More importantly, they lacked the ability to learn or adapt beyond the predefined rules. By the late 1980s, the limitations of symbolic AI, where knowledge was explicitly programmed, became increasingly apparent. The rigid structure of expert systems struggled with incomplete or contradictory information. They couldn't handle the subtlety and variability found in natural language or perception. As a result, AI research began to shift towards new methods that could overcome these challenges. The AI winters had lasting effects on the field. They tempered the early enthusiasm and forced researchers to rethink their assumptions. The setbacks highlighted the complexity of intelligence and the need for more flexible, data-driven approaches. This period laid the groundwork for later advances in machine learning and neural networks, which would eventually transform AI in the decades to come. Looking back, the rise and challenges of AI in the 20th century reveal a pattern of ambitious goals, harsh realities, and gradual adaptation. The journey was never straightforward, but each phase contributed valuable insights. As AI moved beyond symbolic reasoning, it began to embrace uncertainty and learning in ways that more closely resemble human cognition. In the next chapter, we'll explore how these new approaches emerged and how they set the stage for the AI breakthroughs that followed. The story of artificial intelligence is far from over, and the lessons from its early decades remain relevant today. For decades, artificial intelligence was dominated by a clear vision: build machines that could think like humans by explicitly programming rules and logic. This approach, known as symbolic AI, treated intelligence as a set of symbols manipulated by strict algorithms. It was an elegant idea. If intelligence was about reasoning, then why not encode every rule and fact into a machine? Early successes in this field seemed promising. Systems could solve logic puzzles, prove mathematical theorems, and even mimic certain aspects of human language. But beneath the surface, cracks were beginning to show. Symbolic AI struggled to deal with the messiness of the real world, the complexity of everyday situations, the ambiguity of natural language, and the sheer volume of knowledge humans rely on proved overwhelming. Every new domain required painstakingly handcrafted rules, and even then, systems often failed to generalize beyond their narrow scope. The world is not a neat set of symbols. It's noisy, uncertain, and constantly changing. Symbolic AI's rigid frameworks couldn't keep up. This frustration sparked a shift in thinking. Instead of trying to hard-code intelligence, what if machines could learn from data? What if they could discover patterns and make decisions without being explicitly told every rule? This idea laid the groundwork for what we now call machine learning. Machine learning flips the problem on its head. Rather than programming intelligence directly, it builds algorithms that improve automatically through experience. The core concept is straightforward. Feed a computer enough examples, and it can infer the underlying patterns that generate those examples. This approach embraces uncertainty and complexity instead of fighting it. At its simplest, machine learning involves three key components: data, a model, and a learning algorithm. Data represents the examples or observations. The model is a mathematical structure that makes predictions or decisions based on input data. The learning algorithm adjusts the model's parameters to minimize errors or maximize accuracy. Over time, with enough data and computation, the model becomes better at its task. One of the earliest and most influential machine learning algorithms was the perceptron, introduced in the late 1950s by Frank Rosenblatt. The perceptron was a simple model inspired by biological neurons. It took in multiple inputs, applied weights to them, summed the results, and passed the sum through a threshold function to produce an output. The learning process involved adjusting the weights based on errors, nudging the model closer to correct predictions. While limited in complexity, it could only solve linearly separable problems. The perceptron demonstrated that machines could indeed learn from examples. Around the same time, researchers explored other methods like nearest neighbors, decision trees, and Bayesian models. Each brought a different way of capturing patterns in data. Nearest neighbors, for instance, classified new examples based on the closest examples in the training set. Decision trees created a flowchart-like structure, splitting data based on feature values to reach a decision. Bayesian models used probability theory to update beliefs based on evidence. These approaches were more flexible than symbolic AI, requiring less manual rule crafting and better handling uncertainty. The transition wasn't instantaneous or smooth. Early machine learning faced skepticism and technical hurdles. Computing power was limited, and large datasets were hard to come by. Many algorithms were primitive by today's standards, yet the potential was undeniable. Machine learning could adapt to new information, handle noisy data, and uncover insights hidden in complex datasets. One early success came in the field of pattern recognition. Optical character recognition, or OCR, used machine learning to identify handwritten or printed letters from images. Instead of relying on rigid rules about letter shapes, these systems learned from thousands of examples, gradually improving their accuracy. Speech recognition followed a similar path, moving from rule-based phonetic systems to statistical models trained on hours of recorded speech. These applications hinted at a broader truth. Intelligence is less about fixed rules and more about flexible adaptation. Symbolic AI tried to capture intelligence through logic and symbols, but machine learning embraced variability and uncertainty. It treated intelligence as a statistical problem, one that could be solved by algorithms that learn from data. This shift also changed the kinds of questions researchers asked. Instead of, how do we encode knowledge, the question became, how do we represent data, and what algorithms can learn from it most effectively? It opened the door to exploring new models inspired by statistics, optimization, and later, neural networks. By the 1980s, the foundations of modern machine learning were taking shape. Algorithms like backpropagation allowed multi-layer neural networks to learn more complex patterns. Support vector machines emerged, offering powerful ways to classify data by finding optimal boundaries. Ensemble methods combined multiple models to improve performance. Each advance pushed machine learning further from its symbolic roots toward a data-driven future. The consequences of this shift are profound. Machine learning doesn't just offer a new toolkit, it changes how we think about intelligence itself. It acknowledges that knowledge is often implicit, embedded in data rather than explicit rules. It accepts that learning is an ongoing process, not a one-time programming task. Today, this perspective underpins much of what we call artificial intelligence. From recommendation systems to autonomous vehicles, machine learning drives technologies that adapt and improve in real time. But it all started with the recognition that symbolic AI, for all its strengths, had reached its limits. The path forward lay in algorithms that learn from data, not just rules. As we look deeper into machine learning's evolution, the story becomes richer. New models, more data, and greater computational power have transformed what's possible. But the core idea remains the same. Intelligence emerges not from fixed instructions, but from experience. In the next chapter, we'll explore how these early concepts gave rise to modern neural networks and the era of deep learning, reshaping both AI and our understanding of intelligence itself. Neural networks have been around for decades, but their journey has been anything but straightforward. For a long time, they were largely sidelined, seen as intriguing but impractical. Then, something changed. A quiet revolution began, and today, neural networks form the backbone of many technologies we interact with daily. This resurgence is not a coincidence. It's the result of a convergence of ideas, data, and hardware that finally unlocked their true potential. At their core, neural networks are inspired by the brain's architecture, a collection of interconnected nodes that process information in layers. Early models were simple and struggled with complex tasks. The real breakthrough came with a technique called backpropagation. This method allowed networks to learn from their mistakes by adjusting the connections between nodes, layer by layer, refining their performance over time. Backpropagation transformed neural networks from theoretical curiosities into practical tools capable of solving real problems. But even with backpropagation, progress was slow for years. Training large networks required enormous amounts of computation, and the data needed to teach them was scarce. The world had to wait for two critical developments: the explosion of digital data and the rise of powerful, specialized hardware. The internet, smartphones, and connected devices created a flood of information, images, text, audio, unlike anything before. This data became the fuel for training neural networks. At the same time, graphics processing units, or GPUs, originally designed for rendering video games, found a new purpose. Their parallel processing capabilities made them ideal for the heavy mathematical lifting neural networks demand. Suddenly, what once took weeks or months to train could be done in days or even hours. Researchers had the tools to experiment more freely, iterate faster, and tackle problems previously out of reach. With these advances in place, neural networks began to shine in areas where traditional algorithms struggled. Speech recognition, for example, moved from stilted, error-prone systems to fluid, near-human performance. This leap was more than just convenience. It opened doors for voice assistants, real-time translation, and accessibility tools that change how people communicate. The key was the network's ability to capture subtle patterns and nuances in spoken language, something rule-based systems couldn't manage. Image processing saw an equally dramatic transformation. Neural networks started to outperform classical computer vision techniques by learning directly from raw pixels rather than relying on handcrafted features. This shift led to breakthroughs in object detection, facial recognition, and medical imaging. Systems could not only identify objects but also understand context, improving accuracy and enabling new applications like autonomous vehicles and advanced diagnostics. Natural language processing, or NLP, also benefited enormously. Early models struggled to grasp meaning or context, often producing awkward or irrelevant responses. Neural networks, especially when scaled up, began to understand language in a more nuanced way. They could summarize text, answer questions, and even generate human-like writing. This progress reshaped how machines interact with language, making AI more conversational and accessible. The revival of neural networks wasn't a single breakthrough, but a series of interconnected advancements. The right algorithms, vast amounts of data, and powerful hardware created a fertile environment for innovation. Researchers could build deeper networks with more layers, sometimes called deep learning, allowing models to represent increasingly complex functions. This depth enabled AI to tackle tasks once thought exclusive to human intelligence. Yet despite these gains, challenges remain. Training deep networks demands significant resources, raising concerns about energy consumption and accessibility. There's also the question of interpretability. Understanding how these models make decisions is often difficult, which matters in high-stakes domains like healthcare or finance. As neural networks become more embedded in society, balancing their power with responsibility will be crucial. Still, the momentum is undeniable. Neural networks have moved from academic experiments to practical engines driving innovation across industries. They power recommendation systems, enable real-time language translation, assist in scientific research, and even create art. This revival has reshaped AI from a niche field into a transformative force. Looking ahead, the evolution of neural networks continues. Researchers are exploring new architectures, training methods, and ways to make models more efficient and transparent. The interplay between data, algorithms, and hardware remains central, but so does the growing awareness of ethical considerations. The next chapters in this story will likely focus on how we harness this technology responsibly while pushing the boundaries of what AI can do. As neural networks revive and expand their reach, they invite us to rethink intelligence, not just as a fixed human trait, but as something that machines can increasingly replicate and augment. This shift challenges assumptions and opens new possibilities, setting the stage for the next wave of AI breakthroughs. What comes next will depend on how we navigate the complex landscape of innovation, impact, and ethics, and that journey is just beginning. Artificial intelligence has taken a remarkable leap forward in recent years, largely because of a technique known as deep learning. This approach has transformed machine learning from a niche academic pursuit into a technology that's deeply woven into our daily lives. But what is deep learning, and why has it become so influential? At its core, deep learning is a method that uses artificial neural networks inspired by the human brain. These networks consist of layers of interconnected nodes or neurons that process data in complex ways. The deep in deep learning refers to the number of layers these networks have. More layers mean the model can learn increasingly abstract features, allowing it to tackle tasks that were once considered out of reach for machines. Among the most important deep learning architectures are convolutional neural networks, or CNNs, recurrent neural networks, known as RNNs, and the more recent transformer models. Each of these plays a distinct role in how AI systems understand and generate information. CNNs are particularly effective for image recognition. They work by scanning images with filters that detect edges, shapes, and textures. This process mimics how the visual cortex processes information, enabling CNNs to identify objects, faces, or even subtle patterns within images. This capability has driven breakthroughs in fields like medical imaging, where AI can detect tumors or abnormalities often missed by the human eye. RNNs, on the other hand, are designed to handle sequential data. They're well-suited for tasks where context and order matter, such as speech recognition or time series prediction. By maintaining a form of memory across inputs, RNNs can understand the flow of language or the progression of data over time, making them essential for natural language processing applications. Transformers have reshaped the landscape of AI more recently. Unlike RNNs, transformers process data in parallel, using attention mechanisms to weigh the importance of different parts of the input. This design allows them to model long-range dependencies in data, making them incredibly powerful for understanding and generating human language. They are the backbone of many state-of-the-art language models that power virtual assistants, translation services, and content generation tools. The success of deep learning in these areas has been nothing short of revolutionary. In image recognition, models now routinely surpass human-level accuracy on benchmark datasets. In natural language processing, AI can hold conversations, translate languages, and even write coherent essays. In game playing, deep learning-powered agents have defeated world champions in complex games like Go and poker, showcasing strategic thinking that was once thought to be uniquely human. These advances are not confined to research labs. Deep learning is embedded in technologies that many of us interact with daily. Self-driving cars rely heavily on CNNs to interpret the world around them, identifying pedestrians, traffic signs, and other vehicles in real time. Medical imaging systems use deep learning to assist radiologists, improving diagnostic accuracy and speeding up treatment decisions. Virtual assistants like Siri, Alexa, and Google Assistant use language models to understand and respond to voice commands, making technology more accessible and intuitive. Yet, with this power comes responsibility. The widespread adoption of deep learning raises important ethical questions. One concern is bias. Since these models learn from data, any prejudices present in the training sets can be amplified. This can lead to unfair or discriminatory outcomes, especially in sensitive areas like hiring, law enforcement, or lending. Addressing this requires careful dataset curation and ongoing scrutiny of AI behavior. Privacy is another critical issue. Deep learning systems often require massive amounts of personal data to function effectively. Balancing the benefits of personalization with the need to protect user information is an ongoing challenge. Moreover, the opacity of these models, the so-called black box problem, makes it difficult to understand how decisions are made, complicating accountability. The societal impact of deep learning extends beyond ethics. Automation powered by AI is reshaping industries, changing the nature of work, and raising questions about the future of employment. While these technologies can increase efficiency and create new opportunities, they also risk displacing workers and exacerbating inequality if not managed thoughtfully. Despite these challenges, the potential of deep learning remains vast. Researchers continue to push the boundaries, developing models that are more efficient, interpretable, and capable. Techniques like transfer learning allow models to apply knowledge from one domain to another, reducing the need for extensive training data. Advances in hardware and algorithms are making deep learning more accessible and scalable. As you engage with technologies powered by deep learning, it's worth considering the intricate balance behind their capabilities, the blend of engineering, data, and human values that shape their development. Deep learning is not just a tool, it's a reflection of how we teach machines to see, hear, and understand the world. Looking ahead, the journey of deep learning is far from over. Emerging architectures and hybrid approaches promise to expand AI's reach even further. But as these systems grow more sophisticated, the questions they raise about trust, fairness, and control will only become more pressing. Understanding deep learning today gives us a glimpse into the complex future of artificial intelligence, one where machines learn deeply, but we remain responsible for guiding their path. Artificial intelligence is no longer just a tool. It's becoming a force that shapes decisions, influences lives, and redefines industries. But as AI systems grow more powerful and pervasive, they bring with them a set of ethical and societal challenges that are impossible to ignore. How do we ensure these technologies serve us fairly without reinforcing existing inequalities or creating new ones? That question lies at the heart of the conversation about ethical AI. At its core, ethical AI demands fairness. But fairness is complicated. It's not just about treating everyone the same. It's about recognizing and correcting for biases that can be baked into algorithms. These biases often reflect the data used to train AI systems, data that comes from the real world with all its imperfections. When AI models learn from historical data, they can inadvertently perpetuate discrimination against certain groups. This isn't a theoretical concern. There have been documented cases where facial recognition systems performed poorly on people with darker skin tones, or where hiring algorithms favored one gender over another. Such outcomes expose how AI can reinforce social inequalities rather than alleviate them. Addressing bias requires more than technical fixes. It calls for transparency, making AI systems understandable not just to developers, but to those affected by them. Transparency means opening up the black box of AI decision-making, allowing scrutiny and accountability. Without it, how can we trust these systems to make fair choices? And who is responsible when they don't? The question of accountability is critical. When AI decisions impact people's lives, whether it's denying a loan, recommending a medical treatment, or influencing legal outcomes, someone must be answerable for the consequences. Yet, the complexity of AI often obscures responsibility, raising difficult legal and ethical questions. Beyond fairness and accountability, AI challenges our notions of privacy and security. Many AI applications rely on vast amounts of personal data, collected and processed at unprecedented scales. This data fuels everything from targeted advertising to predictive policing. But the more data AI systems consume, the greater the risk of privacy violations. People can be tracked, profiled, and surveilled in ways that were unimaginable just a decade ago. The tension between harnessing AI's potential and protecting individual privacy is a delicate balance. It's a balance that societies are still struggling to define. Security is another dimension that's often overlooked. AI systems themselves can be vulnerable to attacks that manipulate their behavior. Adversarial examples, carefully crafted inputs designed to fool AI, pose real threats, especially in critical areas like autonomous vehicles or cybersecurity. Moreover, as AI becomes integrated into infrastructure and defense, the stakes of such vulnerabilities rise dramatically. Ensuring robust, secure AI is no longer optional. It's a necessity. The societal impact of AI extends deeply into the world of work. Automation promises to reshape labor markets, replacing repetitive tasks and even some complex jobs. This shift raises questions about employment, economic inequality, and the future of human labor. While AI can increase productivity and create new opportunities, it can also displace workers, sometimes rapidly and without clear safety nets. The challenge is not just technological, but social and political. How to manage this transition fairly so that the benefits of AI are shared broadly rather than concentrated in the hands of a few. These concerns have sparked debates about regulation and governance. Some argue for strict rules to guide AI development, ensuring ethical standards are met and harms minimized. Others warn that heavy-handed regulation could stifle innovation and slow progress. Finding the right balance is tricky. It requires collaboration between technologists, policymakers, businesses, and civil society. It also demands a global perspective, since AI transcends borders and its impacts are felt worldwide. One promising approach involves embedding ethical principles directly into AI design. Concepts like fairness, transparency, and accountability can guide the creation of AI systems that respect human rights and promote social good. This means involving diverse voices in development teams, auditing algorithms for bias, and creating mechanisms for oversight. It's a shift from building AI that simply works to building AI that works for everyone. At the same time, public awareness and education are crucial. People need to understand how AI affects their lives and what their rights are in an AI-driven world. Empowering individuals with knowledge can drive demand for better practices and more ethical AI. It can also foster informed discussions about the trade-offs and choices society faces. The ethical and societal implications of AI are vast and complex. They touch on justice, privacy, security, economy, and governance. They challenge us to rethink how we design technology and how we shape the future. As AI continues to evolve, these conversations will only grow more urgent. What remains clear is that technology alone cannot solve these problems. It requires thoughtful, collective effort to steer AI toward outcomes that benefit all of us. Looking ahead, the next chapter explores how different countries and organizations are approaching AI governance. What models are emerging to balance innovation with responsibility? And how might these efforts shape the global landscape of AI development? The answers could redefine not just technology, but the very fabric of society. Artificial intelligence is no longer just a tool confined to labs and niche applications. It's rapidly becoming a part of everyday life, reshaping industries, economies, and even how we think about intelligence itself. But as AI grows more capable, the questions around its future become more urgent and complex. One of the most talked about possibilities is the arrival of artificial general intelligence, or AGI. Unlike today's AI systems, which excel at specific tasks but struggle outside their narrow domains, AGI would possess a flexible, human-like understanding. It could learn, reason, and adapt across a wide range of activities, potentially matching or surpassing human cognitive abilities. The implications of such a breakthrough are profound. It could revolutionize science, medicine, and technology, solving problems that currently seem intractable. At the same time, it raises difficult questions about control, responsibility, and the very nature of intelligence. Researchers are keenly aware of these challenges. The field of AI alignment and safety is dedicated to ensuring that as AI systems grow more powerful, their goals remain aligned with human values. This isn't just a technical hurdle, it's a philosophical and ethical one. How do we encode complex human values into algorithms? How can we anticipate unintended consequences in systems that learn and evolve on their own? These questions drive a growing community of experts who believe that the future of AI must be shaped by careful design and rigorous safeguards. But the future of AI isn't just about machines acting independently. Increasingly, it's about collaboration between humans and AI. Rather than replacing human intelligence, many envision AI as a partner, an augmentation that enhances creativity, decision-making, and productivity. This shift changes the way we think about work and expertise. AI can handle repetitive or data-intensive tasks, freeing people to focus on strategic thinking and innovation. In fields like healthcare, this partnership could mean more accurate diagnoses and personalized treatments. In creative industries, AI might open new avenues for expression and storytelling. Yet, this transformation also brings societal challenges. As AI reshapes the job market, questions about economic inequality and access become pressing. Who benefits from AI advancements? How do we ensure that these technologies don't deepen existing disparities? Governments and organizations worldwide face the task of crafting policies that balance innovation with fairness. Governance frameworks will need to be flexible, transparent, and inclusive, capable of addressing risks without stifling progress. The potential for AI to influence social structures extends beyond economics. It touches on privacy, security, and even the dynamics of power. Surveillance technologies powered by AI raise concerns about individual freedoms. The use of AI in decision-making, from criminal justice to hiring, demands scrutiny to prevent bias and discrimination. These issues highlight the importance of ethical principles guiding AI development and deployment. Looking ahead, breakthroughs in AI are likely to come from multiple directions. Advances in hardware, algorithms, and data availability will continue to push the boundaries of what AI can do. At the same time, interdisciplinary research combining computer science, psychology, and philosophy will deepen our understanding of intelligence itself. This holistic approach is essential for building AI systems that are not only powerful, but also trustworthy and aligned with human needs. The road to AGI remains uncertain, with timelines ranging from decades to perhaps never. But the pursuit itself is reshaping the AI landscape today. Even incremental progress toward more generalizable AI capabilities prompts reflection on how society prepares for these changes. Public engagement and education will play a crucial role in shaping informed conversations about AI's future. In practical terms, we are already seeing early forms of human-AI collaboration in workplaces, creative projects, and scientific research. These examples provide a glimpse into a future where intelligence is distributed across humans and machines, each complementing the other's strengths. This synergy could unlock new possibilities for innovation and problem-solving. At the same time, the governance of AI technologies is evolving. International cooperation and regulatory efforts are emerging to address cross-border challenges. The debate over AI standards, accountability, and transparency is intensifying. Finding a balance between fostering innovation and protecting societal interests is no small task. Ultimately, the future of artificial intelligence is a story still being written. It's a narrative shaped by technical breakthroughs, ethical considerations, and human choices. As these elements unfold, they will redefine not only technology, but the fabric of society itself. What comes next will depend on how well we navigate this complex terrain, how we harness AI's potential while managing its risks. The next chapter will explore the specific ways AI is already transforming industries and what that means for the workforce, creativity, and everyday life. Artificial intelligence has traveled a remarkable path, one marked by both bold ambition and cautious progress. From its earliest conceptual roots in the mid-20th century, when pioneers first imagined machines that could think, to the sophisticated systems we interact with today, AI has steadily reshaped what we consider possible. These milestones are more than just dates or breakthroughs. They represent shifts in how we understand intelligence, creativity, and even humanity itself. The journey began with simple programs designed to mimic basic reasoning. Early machines could solve puzzles or play chess, but their abilities were narrow and brittle. Over time, advances in computing power, data availability, and algorithmic design expanded AI's reach. The introduction of neural networks and deep learning marked a turning point, enabling machines to recognize patterns and make decisions with a level of nuance previously thought exclusive to humans. This evolution was not linear. There were periods of skepticism and slow progress, often called AI winters. Yet each setback laid the groundwork for future innovation, weaving resilience into the fabric of the field. Today, AI touches nearly every aspect of daily life. It powers the recommendations on streaming platforms, helps doctors diagnose diseases, and even assists in designing new materials. Its influence is subtle in some cases and profound in others, but it is always transformative. What makes AI truly remarkable is not just its technical achievements, but the way it challenges our assumptions about work, creativity, and problem-solving. Tasks once considered uniquely human are now shared with machines, prompting us to reconsider what it means to be intelligent. This transformation is not without complexity. AI's integration into society raises questions about ethics, privacy, and control. As algorithms influence decisions from hiring to criminal justice, the stakes become clear. The technology itself is neutral, but its application reflects human values and biases. Understanding this duality is crucial. It calls for vigilance from technologists, policymakers, and users alike. Engaging with AI thoughtfully means recognizing its potential for both benefit and harm, and striving to steer its development in ways that uphold fairness and dignity. Looking ahead, the future of AI is both promising and uncertain. Emerging fields like explainable AI and reinforcement learning hint at systems that are not just powerful, but transparent and adaptive. There is growing interest in collaborative intelligence, where humans and machines work in partnership, each amplifying the other's strengths. This perspective shifts the narrative from competition to cooperation, opening new avenues for innovation. But alongside these technical advances, broader societal questions loom. How will AI shape economies, education, and governance? What new challenges will arise as machines grow more capable? These questions demand ongoing dialogue and reflection. For those watching this unfold, staying informed is more important than ever. AI is no longer a distant concept confined to research labs. It is a force woven into the fabric of everyday life. Understanding its capabilities and limitations empowers us to make better decisions, whether as consumers, creators, or citizens. It also invites us to participate in shaping the rules and norms that will govern AI's role in society. This is not just the responsibility of experts. It belongs to everyone who will live with the consequences of these technologies. Reflecting on AI's journey reveals a story of human curiosity and ingenuity, marked by moments of surprise and challenge. It is a story still being written, with chapters unfolding in real time. The tools and ideas that once seemed futuristic are now part of our reality, and their impact will only deepen. As we move forward, the question is not if AI will change the world, but how we choose to guide that change. The next phase will likely bring new breakthroughs, but also new debates. How will AI balance autonomy and oversight? What roles will creativity and empathy play in an increasingly automated landscape? These are not just technical questions. They speak to the core of what it means to live in a world shared with intelligent machines. Understanding this dynamic will shape the conversations and decisions that come next. In the chapters ahead, we will explore these emerging themes more closely. The story of AI is far from over, and its future will be shaped as much by our values and choices as by algorithms and data. As we continue to navigate this evolving landscape, staying curious and engaged will be essential, because the journey of artificial intelligence is, ultimately, a reflection of our own.